Namaste childrens, welcome to Samveda e-classes, 9th standard number system second session. Dear children, I think you already finished your homework and corrected from your teacher. Congratulations. Now, I will show you the answer for homework. Let compare your answer. Solutions for homework. For the first question, is 0 a rational number? Can you write it is in the form of p by q, where p and q are integers and q is not equal to 0? Yes, it can be written in the form of p by q. The examples are given here, 0 by 1, 0 by 2 and 0 by 3. So, that is why 0 is a rational number. Okay. For second one, find 6 rational numbers between 3 and 4. 3 can be written as 21 by 7. 4 can be written as 28 by 7. See 22 by 7, 23 by 7, 24 by 7, 25 by 7 and 26 by 7, 27 by 7. These are the 6 rational numbers between 3 and 4. Okay. We move on to the next one. Find 5 rational numbers between 3 by 5 and 4 by 5. The solution is here. See, compare your answer. The 5 rational numbers are 19 by 30, 20 by 30, 21 by 30, 22 by 30, 23 by 30. Okay, next move on to the next question. Statements. Every natural number is a whole number. The answer is true. The reason is the natural numbers 1, 2, 3 are all whole numbers. See second one. Every integer is a whole number. The answer is false, because negative integers are not whole numbers. Now, another one, every rational number is a whole number. The answer is false. Why? Because 1 by 2, 2 by 3 etc. numbers are not whole numbers. Okay. Thank you, congratulations, and we move on to the today's very important topic. Locate root 2 on a number line. My dear students, it is very important for your examination purpose. So, locate root 2 on the number line. It is easy to see how Greeks might have discovered root 2. See, consider a unit square OABC with each unit side 1 unit length and draw OB diagonal. See, you can consider 1 unit square OABC and draw a diagonal. See, this is 1 unit, and by seeing this, according to the Pythagoras theorem, we know that the square and the hypotenuse is the sum of the square of other two sides. So, the value of OB is square root of 2. When we simplified, we get the value is square root of 2. So, now what to do? How do we represent root 2 on number line? Now it is very easy. Yes, this is easy. Transfer the square OABC onto the number line, making sure that the vertex O coincide with 0. See, you have to transfer this OABC square onto the number line, making sure that the vertex O coincide with 0. We already know that OB is square root of 2. Now, using compass with center O and radius OB, draw an arc intersecting the number line at the point P. See, draw an arc intersecting the number line at point P. Now, this is square root of 2. This is square root of 2. Now, you can represent in a graph. Here P corresponds to square root of 2 on the number line. Now, you can represent in the graph. You will get the approximation value. The square root of 2 is 1.4 something. Here the approximation is 1.4. Like that you have to represent square root of 2 on a number line. Now, how to represent or locate square root of 3 on a number line? See, you follow the same what you do done it for square root of 2, you follow the same. See, you follow the same. Now, what to do next? Next, construct BD, BD a unit length perpendicular to OB, perpendicular to OB, a unit length perpendicular to OB, and join OD. Now, this is using Pythagoras theorem. We know that OD square is equal to OB square plus BD square. When we simplify, we get the value of OD, that is square root of 3. Using compass with center O and radius R, draw an arc which intersect the number line at point P. See, it intersect point Q. Now, this is Q corresponds to root 3 on the number line. Now, if you transfer this or if you represent in a graph, you will get the approximation value of root 3, that is 1.7. Like this, you have to represent root 3 and root 4. Who is he? The great mathematician Theodorus. He represent square root of 2, square root of 3, square root of 4, square root of 5 up to square root of 17 in a single figure. So, we call this figure as Theodorus wheel. This is, we call it as a Theodorus wheel. We appreciate the contribution of development of mathematics. The Theodorus, this is called Theodorus wheel. We can see here square root of 2, square root of 3, square root of 4 up to square root of 17, he represent in a single graph. My dear students, now real numbers and decimal expansions. In this session, we are going to study the rational and irrational number from a different point of view. We look on the decimal expansion of a real numbers and see if it can be used the expansion to distinguish between rational and irrationals. We will also explain how to visualize the representation of real numbers on the number line using their decimal expansions. Now, rational are more familiar to us. Let us start with them. See, let us take 3 examples: 10 by 3, 7 by 8, 1 by 7. You know the division. Now, we can do together. You can start now. 10 by 3. See, 3 3s are 9. Subtract, we get 1. Now, put a decimal point. Now, you can do it. I will show you. Remainder is here 0. In the first problem, the remainder is 1. Now, we consider third one, 1 by 7. 7 zeros are 0. Now, 1, put a decimal point. Now, 7 sevens are 49. Now, the remainder is 1. Now, if you start again it will start, we will get the answer 14287 and again 14287. You are doing wonderful, congratulations. Let us move on to the further. Dear students, note the values. See what you noticed. Come on, think it once. Can anybody share your views? What you noticed? Okay, I will share you. You should have noticed at least 3 things. What are those? The first one, the remainder either become a 0 after a certain stage or start repeating themselves. This is the first thing you have to notice. Is it right? Yes. Okay. For the second one, the number of entries in the repeating string of remainders is less than the divisor in, for example, in 10 by 3, one number repeats itself and the divisor is 3. In 1 by 7, there are 6 entries 3, 2, 6, 4, 5, 1 in the repeating strings of remainders and the 7 is the divisor. This is the second thing. What is the third one? I will show you. Yes. If the remainder repeats, then we get a repeating block of digits. See here, we are getting the repeating block of digits in the quotient for example, in 10 by 3, 3 repeats in the quotient and for 1 by 7, we get the repeating block, that is I already told you there is 1, 4, 2, 8, 5, 7 in the quotient. And in the example of 7 by 8, we found that the remainder becomes 0 after some steps and the decimal expansion of 7 by 8 is here, there is here 0.875. The decimal expansion of 7 by 8 is 0.875. I will give another examples also. See 1 by 2, the decimal expansion is 0.5. 639 divided by 250, that is 2.556. In all these cases, the decimal expansion terminates, underline the words, or ends after a finite number of steps. We call the decimal expansion of such numbers terminating. What is that? Terminating. Now, my dear students, in the examples of 1 by 3 and 1 by 7, we notice that the remainders repeat after a certain stage, forcing the decimal expansion to go on forever. In other words, we have a repeating block of digits in the quotient. We say that this expansion is non-terminating, recurring, non-terminating, recurring. For example, see here example 1 by 3, when we represent, the answer is 0.33333. See 0.3333 and for 1 by 7, I already told you that is 0.142857. Again repeat 142857. Again repeat 142857. See this is continuous. It never ends. Okay, it never ends. So the usual way of showing that 3 repeats in the quotient of 1 by 3, that is 0.33333, is to write as 0.3, and similarly, since the block of digits 142857 repeats in the quotient of 1 by 7, we write 1 by 7 as 0.14285, where the bar about the digits indicates the block of digits that repeats. Here 3 is repeating, so we put the bar on 3. See 142857 is repeating, so we put bar on 142875. Thus we see that decimal expansion of rational numbers have only 2 choices, my dear friends. What are those? Either they may be terminating or non-terminating, recurring. These are only 2 possibilities, only 2 choices. Either they are terminating or non-terminating recurring. Please note down this very important one. Okay, we move on to the further. See, now suppose on the other hand, on your walk on the number line, imagine you come across a number like 3.142678 whose decimal expansion is terminating the number like 1.2727272727, that is 1.27, whose decimal expansion is, see here 27 is repeating, we put a bar on 27, whose decimal expansion is non-terminating recurring. Can you conclude that it is a rational number? Yes, the answer is yes, it is a rational number. Now, on your walk on the number line, you come across a number whose decimal expansion is non-terminating, non-recurring, is called irrational numbers. My dear students, using these we can get a new definition for rational and irrational numbers. Now, what are those? See, rational number, a number whose decimal expansion is terminating or non-terminating, recurring is rational. We already know that what is a rational number? The number which can be represented as a p by q, we can write it as a ratio of two integers, then we call it as a rational number. Now, we can get the another new one, a number whose decimal expansion is terminating or non-terminating, recurring is a rational. Now, another one is there, the number which cannot be represented in the form of p by q, we call it as a irrational number. Now, here we can get the another one definition here, a number whose decimal expansion is non-terminating and non-recurring is a irrational. See, this is a beautiful one. Please note down, my dear students. Now, some examples, we are going to solve some examples. Show that 3.142678 is a rational number. In other words, express it is in the form of p by q. Both are one and the same, where p and q are integers. My dear students, see, this is a very beautiful and interesting problem. Consider the given problem 3.142678. We can write this one as 3.142678 by 1. Is there any change in their value? No, there is no change in the value is same now. Now, you take that one, multiply both numerator and denominator, what happens? You think? Yes, see, the point is jumping from one digit to another digit. Here the point is moving to right or left, moving to right side, one point is now moved, one point is moved to one digit. Now, see, if you multiply both numerator and denominator by 100, we will get, see, 2 digits is jumped. Now, see, there is a magic, 1000 after multiplying both numerator and denominator, see, 10,000, see the decimal expansion, now it is the decimal point is moving towards right, the digits. Now, see, 10,000 lakh, now 10 lakhs. Now, see, there is no decimal point here. Here 31 lakhs 42,678 divided by 10 lakhs. Now, it is in the form of p by q. Now, it is in the form of p by q. Hence, it is a rational number. See how beautiful it is. Huh? Wow. Okay, we move on to the further. Show that 0.3333 we can represent 0.3 bar can be expressed in the form of p by q, where p and q are integers and q is not equal to 0. See, solution, let 0.3 bar be x. We know that x is equal to 0.333333. Yes. Now, here you have to observe that one digit is repeating. You have to observe the one digit, that is 3 is repeating. So, you multiply x by 10. So, x by 10, that is 10 into x, 10x, 10, x is, we already know that x is equal to 0.333, you have to multiply this, we get 3.333, call this equation number 1. Now, how we represent 3.333? 3 plus 0.3333, now that is equal to 3, in the place of 0.33 you can put x, why? Because x is equal to 0.3333, yes, okay. Now, 10x, take the equation number 1, 10x is equal to 3 plus x. Now, subtract both side by x, we get 10x minus x is equal to 3. Now, simplify, we get 9x is equal to 3. Now, if you simplify, we get x is equal to 3 by 9. Again you simplify, we get x is equal to 1 by 3. See, this is in the form of p by q. My dear students, how it is? It is very beautiful na? Yes, we move on to the further example, very important and interesting example. Now, it is a time for you to solve. Yes, you can solve together. Show that 1.272727, that is equal to 1.27 bar can be expressed in the form of p by q, where p and q are integers, q is not equal to 0. Let 1.27 bar be x. Yes, you can do now. Okay, I will show another step. See, x can be represented as 1.272727. Yes, I think all the students wrote this one. Okay, again, what you have to observe here? Here, 2 digits are repeating. In the previous problem, 1 digit is repeating. We multiply by x by 10. Now, what to do now? Since 2 digits are repeating, we multiply x by 10 or 100. Yes, you are right, it is 100. Yes, 100 into x is equal to 100 into 1.272727. When you multiply, we get the answer 127.272727, that itself. Okay. No, write down, my dear children. I think you are finished. Okay, I move on to the next step. See, 100x, 127.2727 can be written in the form of 126 plus 126 plus 1.272727. So, why? Because in the place of 1.2727 we can put x. That is a magic here. Yes, 100x is equal to 126 plus x. Now, subtract both side by x, we get 100 x minus x is equal to 126, x and x cancels. Now, 99x is equal to 126. Now, you simplify, x is equal to 126 by 99. Further you simplified, we get x is equal to 14 by 11. My dear students, can you think it is in the form of p by q? Yes, it is in the form of p by q. Very good. Okay. Now, find the irrational numbers. We already find the rational numbers between the given two numbers. Now, it is a challenge for you. Find the rational numbers between 1 by 7 and 2 by 7. Its time starts now. You can start now. You can start to solve the problem. Okay, I will show you. So many people are thinking. Okay, solution. It is very easy. We saw that 1 by 7. We already found the solution in this class itself. 1 by 7 is 0.142857. Now, 2 by 7. 2 by 7 can be written as 2 into 1 by 7. So, in place of 1 by 7, what we can write? Yes, you are right. We can write 0.142857 multiply by 2, we get 2 by 7 is equal to 0.285714. Yes, you are right. Now, you can write the irrational number between 0.142857 and 0.285714. Now, can you write? Yes, you can start. I will show you. See, these are the two irrational numbers. Now 0.150150015000000, you can write whatever it, but it should not be recurring, it should not be repeating. Okay, non recurring and non repeating terms you can be write. Okay, we can find the number which is non terminating and non recurring lying between them. Now what we learned today, my dear children? Okay, just we recall what we learned. Okay, locate root 2 and root 3 any number line, we already located. Okay, real numbers and their decimal expansions and some problems we solved, and find an irrational number between two irrational numbers. See, in the previous class we find rational numbers between two rational numbers. In this class we find the irrational numbers between irrational numbers. So, between two rational numbers there is a infinite number of rational numbers, between two irrational numbers there is a infinite number of irrational numbers also there. Now it is a time for homework. Now my dear students, write down exercise number 1.3. Write the following in the decimal form and say what kind of decimal expansion each has. See, this is very important. What kind of decimal expansion each has? Problem number 1, 36 by 100, second one 1 by 11, and also second one, express 0.6 bar in the form of p by q, where p and q are integers, q is not equal to 0. You can express in the form of p by q. Okay. Okay, next one, locate square root of 5 on the number line. I already showed you the Theodorus wheel. First you have to locate root 2, root 3, root 4, then after root 5. Now find the irrational numbers between 5 by 7 and 9 by 11. In the next class, what we are going to learn? Representing real numbers on the number line. Here also we represent the real numbers. In this class we represent irrational number in the number line. Operations on real numbers, addition, subtraction, multiplication and divisions of real numbers, and locate square root of 3.5 on a number line. Loss of exponents for real numbers. We already know, you prepare a chart of loss of exponents, what you learned in the 8th standard. Okay, it will use for the next class. You list it out and be ready for the next class. Loss of exponents for real numbers, and also ready with geometry box and graph sheets. Okay, thank you. You complete your homework and show your maths teacher. So, if you want to learn mathematics easily, you can practice. Okay, we can meet you on the next class. Thank you.